screen. Today we are going to extend probabilistic view of regression towards non-independent priors and noise. We're going to first review weighted least squares. We started on this last lecture. Then we're going to talk about maximum likelihood estimation with dependent noise. And this extends least square regression to so-called generalized least square, GLS. And then we're going to talk about MAP, maximum posterior estimation with dependent weights. You don't just have Gaussian distribution in the noise, but also in the model space. And only MAP deals with that. That's why it's MAP with dependent weights. And we are going to talk about Tikhonov regularization. Weighted least square is naturally introduced through an optimization point of view, where not every instances are created equal. Each instance has domain variable x, target value y, but also has a weight. And we introduce the scale. Usually weight is a non-negative number, so it's the weight is the square of the scale. Instances with larger weights are usually the ones that you have higher confidence in these measurements, and you want them to be evaluated. The prediction errors on these points, you want them to be valued more. You want them to be precise. So that's translated into the least square prediction error. You want to give more weights to these terms. So each prediction error, this is the least square prediction error for each instance. And you want to weight by the weights that are given to you for each instance. And in the matrix form, this is what we know of, and this is just a diagonal matrix. When it's very straightforward translation into the matrix form. And then if you look at the math, you just multiply this into each term here, and you get SS linear combination of that. Target value becomes S scaled version Y. And that is something we know. S is known, X is known, Y is known during training. So it's just as if you modify the data going from XXY, instead of XY, you turn them into SX and SY. So weighted least square is equivalent to least square with scaled data. In a way, it's a little bit it's as intuitive, but not so intuitive. Because think about this. Initially, X and Y, they are at equal footing. They are in the universe of the same units. Now each instance gets to be scaled by individual weights. And some could be scaled by 1, some could be by 2, some could be 10.5. So you can see these points all diverge everywhere. The original shapes are no longer preserved. What they're saying is, if you think that the weights are associated with every instance, the equivalent least square fitting problem is just as if they are scaled accordingly, and then you fit a line in an unweighted fashion. In terms of math, it's straightforward. So one particular case is S going, if you just repeat an instance, right? In a way you can think of this, if this weight is twice as important, why don't you just add another X or Y, which is identical to that? repeat an instance, right? And that actually corresponds to weight by square root of 2, right? Because you, in the end, if you have individual instances, this term will be repeated twice. So the corresponding scale here will be square root of 2. That's just the criterion itself. So by the same token, if the weight is, say, 3 or 4, right? Any number, you can think of it, just repeat the same instance for some fractional number of times. So, and we can also take a maximum probabilistic view of this weighted least square. One way to derive this is to model the fact that some data are noisier than others. So instead of the usual least square, the noise is IID. They all follow the same distribution. We assume that each noise has its own standard deviation. Here is very straightforward. This can be understood as some unit normal distribution multiplied by scale factor sigma I. Sigma I here is unknown, but fixed for each instance. Then, taking this equation, you divide it both sides by sigma. You divide by sigma I on both sides. Then you obtain this equation. And now the noise, again, is IID. That's the form we know of. This is exactly this. The only, it takes the same form, and here you have a unit standard deviation. This is some unknown but constant Gaussian noise spread. So from this perspective, you also reach the same conclusion. Least square with weighted least square is simply least square with scaled data plus some unit Gaussian model. A third view of getting to the same conclusion is just go for the MLE directly. Since each noise model becomes Zi, following the normal distribution with its own sigma I, when we derive the maximum log likelihood estimation, each term is taking its own sigma I. In the past derivation, we have the same constant. Now it becomes sigma I. But this term, and here also becomes sigma I instead of sigma. But this term has nothing to do with f. So when you try to maximize over f, this term is irrelevant. So it becomes this. Again, you reach the same conclusion. Weighted least square is maximum likelihood estimation with independent individual Gaussian noises. And from this equation, you can see that in the weighted square, we have Si squared